video game is a combination of graphics, audio, user interaction, game logic,
That's it, you got it.
sometimes AI, sometimes networking, and almost always some form of physics. Even games from the early 80s relied on basic physics calculations to simulate motion and interaction. Today, physics engines are virtually indispensable, whether built in-house or integrated from external libraries. I've been creating tutorials on this channel on the topic of OpenGL and Vulkan for more than 4 years, and I always wanted to explore physics alongside 3D rendering, to build not just what you see, but how it behaves. Over the years, I've accumulated a solid collection of books on physics simulation, and now it's time to put them to good use. In this new series, I'm hoping to create a physics engine with support for rigid body dynamics, collision detection, projectiles, spring systems, and a variety of vehicle simulation. Such algorithms can be useful for many games. Before we get started, I'd like to say a big thank you to Shasta, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. Most of the objects we'll be working with, whether people, monsters, vehicles, or buildings, have a physical presence that can be represented in 3D space. They possess width, height, and depth, making them suitable for spatial modeling. The exceptions are elements like smoke or other particle effects, which are small enough that their physical bodies can be ignored. To simplify things at the outset, we'll treat all objects as particles. A particle, in this context, is simply a geometric point in space. Each object in our physics system will be associated with its own particle, representing its position in 3D space. This approach aligns well with how we've been handling 3D rendering so far, where each object already has a position attribute. In our physics system, we'll refer to this position attribute as the particle itself. As the series progresses, we'll evolve beyond this simplified model and explore more complex ways to represent physical bodies, including rigid bodies, collision volumes, and articulated systems. Let's start by studying a few basic concepts in the field of kinematics, which is the study of motion in the absence of forces. You can think about it as the mathematics of motion, and it helps us analyze systems of objects and predict where and when they will move. 1D kinematics is applied to a particle traveling along a straight line. The first key concept in kinematics is velocity, which describes how much distance an object travels over a given period of time. It is calculated using the following formula, where delta x is the change in position, or distance traveled, and delta t is the time interval during which the motion occurred. This gives us the average velocity over that time period. You may recall from middle school that speed is defined as distance divided by time. So what's the difference between speed and velocity? The crucial distinction is direction. Speed is a scalar quantity. It tells you how fast something is moving, but not where it's going. For example, your car's speedometer shows your current speed, but it doesn't care whether you're heading north or south. Velocity, on the other hand, is a vector. It has both magnitude, which is the speed, and direction. In our physics system, each particle moves along the direction defined by its velocity vector. We can visualize a car's motion by plotting a graph where the x-axis represents time and the y-axis represents distance traveled. Sometimes the graph rises steeply, indicating rapid movement, and sometimes it flattens out, meaning the car has stopped and the distance isn't changing. While we can calculate the average velocity over the entire graph, it becomes much more insightful to examine velocity over smaller and smaller time intervals. As we zoom in on different segments of the graph, the velocity varies depending on where we measure it. To find the instantaneous velocity, the speed at a specific moment, we shrink the time interval as much as possible. Although we can't make delta t equal to 0, since division by 0 is undefined, we can express this idea using a limit. In calculus, this is written more compactly as follows. This notation represents the derivative of position with respect to time. We can take things a step further by examining how velocity itself changes over time. By plotting a graph of velocity versus time and calculating its derivative, just as we did with position, we arrive at a new quantity, acceleration. Acceleration is the rate of change of velocity with respect to time, and it's measured in meters per second squared. This unit means that for every second that passes, the velocity increases or decreases by a certain number of meters per second. You might wonder why we say second squared. Here's why. Velocity is distance over time, and acceleration is velocity over time. So acceleration becomes the following, which involves time squared in the denominator. In practice, this relationship is captured by a well-known equation from classical mechanics that calculates the position of a particle under constant acceleration, where p0 is the initial position, v0 is the initial velocity, a is the constant acceleration, and t is time. However, in real-time simulations, especially in video games, we often work with very small time steps. For example, 16 milliseconds per frame. Squaring such small values and multiplying by a half can result in tiny fractions that may be negligible or cause numerical instability. To simplify, we use a more practical approximation for updating position. This linear update is computationally efficient and works well for small time steps, especially when acceleration is handled separately. In the context of 1D kinematics, we focused only on motion along the x-axis. This simplifies our equations and helps build intuition. But real-world motion often occurs in 2 or 3 dimensions, so we can naturally extend these concepts to 2D and 3D kinematics by incorporating the y and z axes. Because the x, y, and z axes are mutually perpendicular, we can treat motion along each axis independently. That means we can apply the same kinematic equations to each axis separately. Each component, position, velocity, and acceleration, becomes a vector with x, y, and z parts. Now, kinematics is interesting on its own, but in the real world, nothing moves unless a force acts upon it. Sir Isaac Newton laid the foundation for this shift with his 3 laws of motion. For now, we'll focus on the first 2, which are directly relevant to understanding how forces influence motion. We'll save the 3rd law for later discussion. So once we introduce forces into our system, we've officially stepped out of kinematics and entered dynamics, which explains the title of this video. Newton's first law of motion states that a body remains at rest or in motion at a constant speed in a straight line unless acted upon by a force. This principle is known as the law of inertia, and it captures a fundamental truth about how objects behave. They naturally resist changes to their state of motion. A stationary object won't start moving unless a force pushes or pulls it. A moving object won't slow down, stop, or change direction unless a force interferes. In other words, objects tend to mind their own business, staying still or moving steadily, unless something compels them to do otherwise. Newton's second law of motion states that the net force on a body is equal to the body's acceleration multiplied by its mass. This law is expressed mathematically as follows, where F is the net force in newtons, m is the mass in kilograms, and a is the acceleration in meters per second squared. Mass represents the amount of matter in an object and reflects its inertia, its resistance to changes in motion. For example, it takes significantly more force to accelerate an aircraft carrier than a car because the carrier has much more mass. Force is measured in newtons. 1 newton is defined as the amount of force required to accelerate a 1 kilogram mass by 1 meter per second squared. This law forms the backbone of classical mechanics and is essential for simulating realistic motion in physics engines, from falling objects to colliding vehicles. So that was hopefully a gentle introduction to the field of particle dynamics. In the next video, we will dive into the implementation and see how it works in practice. Thank you for watching, and I will see you next time.